Okay, we're going to write insert, and we're going to insert a key into a binary search tree in our Racket data structure. And again, we're going to use this main reasoning strategy about thinking about trees as recursive. We've got a naturally recursive structure, and we're going to take the perspective of a single binary search tree or a single tree and realize that as a single tree, we have a key and then a left and right subtree. Okay, here's the algorithm for insert that we looked at before. You'll notice that 2A and 3A, those are both if we get to the case where we get to an empty subtree. And in that case, we just add it right there. So we're going to be looking at 4 cases: an empty case, a case where we find it, a case where it's smaller, and a case where it's bigger. Here I've got the helper functions that you can use to try and write this, and I want you to try and write I want you to write the function insert that will take an element and a tree and insert that element at the right spot into that binary search tree. Okay, so pause it here. Okay, so here I am trying to write insert, and if you haven't already tried, pause. I'm going to give myself a cons because I know I'm going to have those 4 cases to work with. Okay, and before I get started even, I'm going to label each of those cases. So the first one is going to be my empty. The second one is going to be found it. The next one is going to be less than, and the last one is going to be greater than. Okay, so if I'm trying to insert E, that's my element that I want to add, into an empty binary search tree, then I need to make a new leaf. So empty tree, if that BST is an empty tree, then I want to make BST leaf with that element E. Okay, how would I know if I found the element? That would mean that that E was equal to the key of the current BST. And in that case, if I found it, then I just want to return the current BST. I don't want to change the structure at all. Okay, next, how do I know if E is less than and should go in the left subtree? Well, that means that E is less than the key of the BST. And in that case, I need to call insert on the left subtree. Okay, so I know that I need to call insert with E and the left tree of the BST, but this is a really important piece. If I only return insert E on the left subtree, then anyone who calls insert will only get the left subtree back, so I'll essentially be throwing away the current key and the right subtree. I can't only return the left tree, I need to return the whole tree. So I need to call make BST, and that takes 3 arguments. It'll take the key of the current BST, the new left tree, and then the new right tree, but that one's actually not changing, so we can just call right tree BST. Okay, so when I want to add it to the left subtree, I actually have to make a new binary search tree, similar to how we had to make a new pair or call cons whenever we were adding something to a list. So I call make BST with the current key, I insert it into the left, and then I leave the right unchanged. In the case where it's greater, it's going to look super similar. I'm going to make a BST. The key will be whatever the current key is. I'm going to keep the left tree unchanged. And then the right tree, I need to insert E into that right tree. And oops, I was missing one more parenthesis. And I'll move these comments up a line because I think they're a little confusing when they're at the bottom. Okay, so there were my 4 cases: empty, found it, less than, and greater than. If we want to think about the fact that we have to keep calling make BST, it's really similar to how we had to keep calling cons in increment all. Let's look at that code. Okay, we were taking apart our list using rest and first, and so we needed to put it back together with cons. And similarly here, I'm taking apart my tree with left and right, and I have to use make BST to put it back together. Oh, I'm using key left and right to take it apart, and I have to use make BST to put it back together. So now that we've got this tree structure, it's a little more complicated, but we're using all these same ideas from when we were working with linear lists.